In this class, we have already talked about atoms of different elements coming together to form compounds. In this lecture, we will discuss how this happens in more detail. Remember that all compounds can be subdivided into ionic compounds, in which electrons are transferred from one atom to another to form a cation and an anion that are held together by electrostatic interaction, and molecular compounds, in which electrons are shared between two atoms. Let's discuss ionic compounds first. An example of an ionic compound is sodium chloride, table salt. Let us watch the formation of sodium chloride from solid sodium metal and chlorine gas.
We've asked Lonnie to demonstrate the formation of an ionic bond. In this case, the bond between sodium and chlorine in sodium chloride. So Lonnie's filled a beaker with elemental chlorine. That's chlorine gas, Cl2. It's a yellow gas. He'll also use solid sodium metal. Solid sodium metal is a shiny silver metal that's very soft. He can actually cut it with a knife. Sodium metal is very reactive. It will react in air and water, so it's stored under hexane. He'll pull off a small chunk and immediately store it under hexane while he prepares the rest of the experiment. Now, to get the reaction to go, he'll want to clean the sodium, make the surface very clean, and warm it slightly to help the reaction proceed. He'll do that by placing the sodium in a spatula and then warming it over a flame to clean the surface and to get the sodium warm enough to initiate the chemical reaction. The reaction goes because the positive ions formed on sodium and the negative ions formed on chlorine are drawn together, a Coulombic interaction, to form an ionic bond. Now the reaction between sodium and chlorine, of course, forms sodium chloride. We typically know that as table salt.
So what happens to electrons in this synthesis of sodium chloride? Initially, sodium atoms in the metal have all of their electrons. Because the number of negatively charged electrons is the same as the number of positively charged protons in the atomic nucleus, the net charge of the sodium atoms is zero. Because the two chlorine atoms in the diatomic molecule of chlorine gas are identical, the electrons in the chlorine molecule are equally distributed between the two atoms. Each atom has as many electrons as it has protons in the nucleus, so the net charge on each chlorine atom is also zero. Once the reaction between sodium and chlorine occurs, one electron from each sodium atom is taken away and transferred to a chlorine atom. Therefore, a sodium cation with a net charge of 1 plus and a chloride anion with a net charge of 1 minus are formed. This is an oxidation-reduction reaction, since a transfer of electrons from one substance to another occurs, and the charge states of the atoms involved in the reaction change. But why are electrons transferred from the sodium to the chlorine? It turns out that atoms or ions are most stable when they have 8 electrons, referred to as an octet, in their outermost shell. The outermost shell that has any electrons in a neutral atom of an element is referred to as the valence shell. If we write the electron configuration for all atoms in the periodic table, we will find that the noble gases, except helium, have 8 electrons in their outermost shell. Noble gases do not readily react with other elements. Other elements can go to a more stable state by gaining or losing electrons. For instance, sodium has an atomic number of 11. Its electron configuration is 1s2, 2s2, 2p6, 3s1. It has one more electron than neon, the noble gas that precedes it. That one extra electron is the only electron in the third shell. Chlorine has an atomic number of 17. Its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p5. It has one fewer electrons than argon, the noble gas that succeeds it. It has 7 electrons in the third shell. If sodium donates its only electron in the third shell to chlorine, forming a sodium plus cation, then its outermost shell that has any electrons will be the second with a total of 8 electrons. When chlorine accepts the electron from sodium, it will form a chloride minus anion. The extra electron will be added to the 7 electrons in the third shell to bring the total up to 8, so both sodium plus and chloride minus then get stable electron configurations with 8 electrons in the outermost shell, like those of the noble gases, that of neon for sodium plus and that of argon for chloride minus. Note that by donating an electron, sodium does not turn into neon, and by accepting an electron, chlorine does not turn into argon, because the chemical identity of an element is determined by the number of protons in the nucleus that doesn't change. Rather, a sodium cation and a chloride anion are formed. Gilbert Lewis, a famous American chemist who served as a professor and dean of the College of Chemistry at UC Berkeley for many years, proposed a convention for representing electrons in the valence shell of a chemical element, referred to as valence electrons. In this convention, known as Lewis dot structures, valence electrons are shown by dots. The dots are placed on all 4 sides of the symbol of a chemical element, at the top, the bottom, left, and right. 1 dot is placed on each side before a second dot is placed on any side. No more than 2 dots can be placed on any side, so the total number of valence electrons for the element does not exceed 8. So here are the first 3 periods of the periodic table, and here are the Lewis dot structures of the elements in those periods. As we said earlier, the noble gases, except helium, have 8 valence electrons, a complete octet. Helium has 2 electrons in the first shell. The first shell only contains 1 orbital, 1s, and therefore cannot hold more than 2 electrons. Therefore, helium has a completely filled first shell, 2 electrons, and this is referred to as a duet. Other elements can lose or gain electrons in order to obtain the same electron configurations as the noble gases. Depending on the compound that it is part of, hydrogen can lose its only electron or can gain another electron to get a duet like helium. Lithium and beryllium tend to lose 1 or 2 electrons respectively to also end up with a duet in their first shell. Other elements can lose or gain electrons to get an octet. Lewis dot structures offer a convenient method for visualizing how electrons are transferred in ionic compounds. Let's look at how to draw the Lewis dot structure of an ionic compound using the example of sodium chloride. The first step is to write the Lewis dot structures for the metal and the nonmetal, sodium and chlorine in this case, side by side. Then the valence electron from the metal should be transferred to the nonmetal. When this is done, chlorine has an octet in its valence shell, and the valence shell that held sodium's only electron, the third, is now empty, and the preceding shell, the second, has an octet. The final step in writing the Lewis dot structure of an ionic compound is indicating the electric charges of the cation and the anion, given by the number of electrons lost or gained. The anion with its octet is written in brackets, and the charge of the anion is indicated outside these brackets. In another compound, sodium hydride, the only electron in the valence shell of sodium is transferred to hydrogen, giving it a duet. In different compounds, hydrogen can either gain or lose electrons. For instance, in hydrochloric acid, it gives up its only electron to chlorine. Whether an atom loses or gains electrons in a compound is determined by a quantity called the electronegativity. Electronegativity is a measure of the tendency of an atom to attract electrons. Electronegativity exhibits the following periodic trends. It increases as we go right within a period and decreases as we go down within a group. There are some exceptions to this rule. Noble gases that do not readily form compounds, transition metals for which the electronegativity varies relatively little, as well as F-block elements, the lanthanides and actinides, that generally have complex chemical properties. Electronegativity is a dimensionless quantity, meaning that it has no units. It is a property of a chemical element. When considering a pair of elements that form an ionic compound, to determine which element transfers its electrons to the other, it is necessary to compare their electronegativities. The element with larger electronegativity will take electrons from the element with smaller electronegativity. Electronegativity values have been systematically determined for chemical elements in 1932 by the American chemist Linus Pauling. Pauling was one of the most prominent chemists. He was awarded a Nobel Prize in Chemistry for developing the theory of chemical bonding. He also received a Nobel Peace Prize for his advocacy for nuclear disarmament and vocal opposition to weapons of mass destruction. His wife, Ava Pauling, was a civic activist who convinced him to get involved in these issues. Looking at the electronegativity table, you can see that nonmetals generally have larger electronegativities than metals. Therefore, nonmetals accept electrons from metals and form anions, and metals donate electrons to nonmetals and form cations.